Thank you very much, Avke, for the kind introduction. So I'm going to do my best today to unfortunately make up for Christoph Hartmann, who can't be here, and to discuss a little bit our collaborations with Nestlé. So as Avke said, I lead the Create Lab at EPFL, and we really focus on developing new design, fabrication, and computational approaches for developing robots that can interact with the environment in more fluid ways. But today, I'm going to talk about robots related to agriculture and food. So how we can deploy our robots from farm all the way through to the food we eat. But first of all, I think we need to look at why is this important? Why should we, as roboticists, care about agriculture? And if we look at the situation in Switzerland, we're already using 30% of land to create our food. And this is becoming increasingly challenging to generate enough food to feed the population. This is under pressure because of climate change, growing populations, etc. And this is already leading to a significant contribution of greenhouse gases within the country. So we need to do better in creating more sustainable, more efficient land use, and more efficient resource use. We're also in a really unique position that we have many leading food industry and technology companies here. So we've got some huge opportunities to rethink our food systems. And resulting from this, in the last month, there's been a really interesting new strategy piece for climate and agriculture in Switzerland, that by 2050 we need to reduce greenhouse gases related to the food industry by 2/3 and also reduce meat consumption. And this is interesting because this has significant both health benefits and sustainability benefits. So, if we can look at how we can integrate robotics into food systems to rethink these practices, we can have significant potential and advance our systems in terms of both reducing the environmental impact, making agriculture and food more sustainability, whilst also significantly contributing to health and well-being. So today, I'm going to try and talk through a little bit of how we can apply robotics right from farm and kind of the growth of our food to the end stage when we as consumers hopefully enjoy what we get to eat. And hopefully, I want to motivate all of you that agriculture is something as roboticists we need to get engaged with. We need to help solve these really urgent and pressing problems. So firstly, looking at how we can apply robotics in the farm to both improve food security, reduce waste, and also maximize the nutritional value. One of the first things I think probably quite a few of you in this room are maybe looking at is harvesting. So there's increasing issues in terms of getting reliable sources of labor, which is leading to a lot of crops going wasted in the field. And also, actually, our harvesting systems are quite inefficient and often don't promote good shelf life or even nutritional value of our crops. So moving to more robotic approaches for harvesting could really improve the quality of our food and also improve the sustainability aspects. But it's a challenging problem. We're in unstructured environments. There's a lot of uncertainty. And also, it requires extensive field work. So we've been looking at how for delicate crops, such as the raspberry, which are only ripe for very short periods of time, can we develop actually soft sensorized training tools for our robots so they can actually learn in the lab? So we've developed what we're calling our soft robot raspberry physical twin that has embedded soft sensors. This allows both a human to demonstrate a tactile demonstration of this task, and for our robot then to iteratively learn on this physical simulator how to perform this and to minimize the gap between our human demonstration and our robot performance. And our idea is if we then close our reality gap between our soft raspberry and the real ones, we can not only train our controller for harvesting this delicate fruit, but we can also train our vision system. So here then we can, with zero in-field training, only lab training, we can come to the field and show dexterous, delicate harvesting of this challenging crop. And this allows us to rethink harvesting with robots on board. We can do it at night, for example, when the water content is higher, promoting shelf life. We're also working with some collaborators on blackberry harvesting, showing already that actually robotic harvesting over humans vastly increases the shelf life. But one issue with agriculture is every crop is different. Now, ideally, we would have a fantastic, dexterous robotic hand that could be used for all crops, but at the moment, we still need some specificity to the crop. So we've been looking at how we can use computational methods to accelerate the development of bespoke robot grippers for agriculture. And one of those kind of concepts is looking at how we can use recent advantages in LLMs even to promote more fluid and rapid development of bespoke robot grippers, for example, for tomato harvesting. But in order to be able to harvest crops, we have to have food. And our food system is so inherently tied to our climate system. We need to have insects to perform pollination. We need to have water, but not too much that we have flooding, and we need to have some ability to predict the kind of weather we're going to have. So the other big contribution where robotics can make is working with climate scientists, biodiversity experts, looking at can we get better predictors of climate change, weather predictions, and actually use robots perhaps even to promote biodiversity. So we've been working with some experts in both climate science and biodiversity to try and develop robots that can autonomously explore these harsh environments for climate and biodiversity sensing. So for example, we're looking at creating some robots that can be deployed into big chimney-like moulin structures in glaciers to perform 3D scans so we can reconstruct these chimneys and better predict water flow. We're also developing some autonomous, compliant folding morphing robots that can go in a variety of terrains, including very steep terrains, water, and utilize their morphing and compliant capability to simplify the autonomy required, such these things can then go and collect data, samples from really challenging conditions. And we're also working on making modular robots for biodiversity monitoring. Can we collect information about the insects present in our farm systems such that we can predict likely challenges in pollination, or even try and improve the presence of pollinators in our agriculture environments? So, following the development of food, the next part of the food chain is really about design of food products. How can we create food that is safe to eat, it's nutritious, and also offers sustainable solutions? And this is a challenging problem because we need to satisfy many constraints. And this is a project we've been very lucky to work with Nestlé on, looking at how we can use robots to help automate the development of new, novel food solutions that make use of more plant-based ingredients. And plant-based recipes is something that's quite still new to the food science community, and we've got many different options. So we have a really large design space. So we're looking at combining our robotic automated food scientist, which can combine dry, wet ingredients, perform various processing conditions in terms of heating, mixing, and also automate the measurement. Not only can we show greater repeatability and precision in this experimentation, we can also combine this with online optimization to identify novel recipes, be it single objective or multi-objective. And so, for example, with this, we can actually find recipes which are somewhat unintuitive to perhaps what would be predicted by kind of food science intuition, and also can offer interesting benefits where we can have compromises in terms of the nutritional value and also cost, for example. So this, I think, is a really exciting direction for robotics and the development of novel food products. But as we all know, it's not all about the viscosity of your food, the protein content. The perception of food is so important. And perception is something we talk about as roboticists a lot. But we don't often talk about perception of food. And it's a fascinating area because it's so multimodal. It's visual, it's tactile. The receptors in our tongue are kind of more impressive in some ways than those we have in our hand. So it's really interesting trying to look at, can we develop robots that could have similar perception of food systems? So we've been looking at how we, for example, can bring tactile perception to a soft robotic tongue to be able to get some idea of the mouthfeel or the perception of texture of food. And also more on the safety side, looking at mimicking, for example, our swallowing system. So can we use this to detect or predict any hazards that might come from food products, for example, that could lead to choking or other hazards? And the final stage, of course, is then cooking and preparation, and how we can create novel robots that can assist us and to make this task even more enjoyable. So here, for example, we're looking at using our Adapt hand, which has distributed compliance at the skin, joint, and wrist level to automate the creation of food baking, with the idea that this could sit along humans to either provide assistance to those that don't have the dexterity or even improve the processing of this task. And even on the feeding side, Can we develop robots that can be assistive, help those in terms of caregiving, maybe in terms of even creating soft robots that are sufficiently compliant that as humans we're happy to have our food, obviously fondue, we're in Switzerland, fed to them. So here we're looking at the developments in our architectured soft robot arms to look into feeding and bringing the interactions between humans and robots much closer. So, hopefully I've given you a very quick idea of the range of robotics tasks there are, right from harvesting through to the preparation of food. And what I'm really excited about in the future is how can we actually use robots to close the loop on waste on the carbon cycle? Can we use robots to automate and optimize the collection of waste food and also recycle this CO2 to create the future food systems which are more sustainable, healthy, and nutritious? So just to conclude, I want to say agri-food is really a challenging problem that we need to address. And it's really important that robotics is part of this conversation. It is one of the tools we have to address this. And I think in Switzerland, we're really well positioned to be a leader in this area. And we also have some unique opportunities which we can leverage. So I just want to finish by really acknowledging the fantastic students, postdocs, and collaborators in my group that have produced all of this work. They're really fantastic, inspirational to people to work with. And to say, please do come and visit us. We're upstairs on the gallery area where we have all the robots I've shown today to demonstrate and some others as well. So thank you very much for listening, and hopefully see you later at the booth.
So thanks a lot for the very inspiring talk and impressive talk. So let's take time for questions, comments from the audience. Yes, there is one there. Just wait for the mic. If you can raise your hand again, and the mic is coming there. Yeah.
Hi, Josie. Hi. Thank you for an inspiring talk. I'm actually doing a master's in food security, so this is really, really cool, everything you're doing. Just one question regarding agroforestry and intercropping. Can you foresee novel harvesting solutions using robotics in an open broadacre context, resolving the challenges with harvesting in agroforestry and intercropping, where in conventional tech you need to consider for one crop over the other?
I think that's a really interesting point, because I think if we can develop robots that can navigate in these kind of terrains, that have the autonomy, we can move away from just having very kind of monoculture fields, where we don't have hedgerows, we don't have fields. So if we can co-design our agriculture environment with our robots, I think then we can move to far more sustainable approaches where we consider the biodiversity and all aspects of plant health into this design. So I believe that is the future. I think we've got a little way to get there, but I think it's a really exciting vision for this co-design of the actual agriculture systems with the robots.
Any other question? Maybe while people think about it, I'll take the opportunity to, I didn't know this mouse robot that you developed, so that's quite incredible. How do you validate the perception part? How do you know what it perceives is similar to what humans perceive?
Exactly, there's a challenge there in getting a ground truth that is meaningful. So currently, a lot of food science trials rely on human studies and getting qualitative feedback from this. So there's going to be a big challenge in how do we validate these results in terms of ground truth and validating against user panels, be it questionnaires. The other thing we could use to some extent is simulation and mechanical modeling for some aspects, but that's still, we have a significant sim-to-real gap. So at the moment, we're looking at validating against human sensory panels.
Okay, any final question from the room? If not, I'll take the opportunity to take it.
Thank you.
I didn't see so many humans here, and for sure agriculture is a human-intensive task. So how do you see the collaboration between human workers and your robots?
Very good point. So I think harvesting is a nice example that we can move from having humans having to do this monotonous, quite physically challenging tasks, to having the humans perhaps involved in grading or other tasks where they're less physically demanding, but we can still leverage some of the capabilities of humans in terms of our ability to respond to uncertain or unknown events. So I think we really need to see humans as assistive in terms of agriculture, especially in the next kind of 3 to 5 years.
Great, so let's do a big round of applause for Josie. Yeah.